What's going on? I'm Muhammad Abu Mandur. In the following few minutes, I will try to build some intuition about the historical context of the transformers, not just how they work, but instead dive into the evolution from simple RNN models to the groundbreaking transformer models. So let's not waste any time and dive in.
Before we dive into transformers, let's go back to where the idea of attention first emerged. Here you're looking at an email exchange between Dmitry Badanow and Andrei Karpathy. Back then, machine translation relied heavily on sequence-to-sequence models, built with recurrent neural networks. As Dmitry observed, they ran into a major roadblock. How do we avoid the bottleneck between the encoder and decoder? Dmitry's breakthrough solution was to give the decoder the ability to look back at the source sequence, much like we naturally shift our gaze when translating between languages. And just like that, attention was born, a mechanism that would lay the groundwork for transformers and revolutionize the field of natural language processing forever. Now let's look at the abstract of our main paper. Attention is all you need. This marks the moment transformers were first introduced to the world. It kicks off with the dominant sequence transduction models are based on complex recurrent or convolutional neural networks, but hold on, what's a sequence transduction model anyway? Back in the early days, most models like deep neural networks, DNNs, demanded fixed-length inputs. That wasn't exactly convenient since we had to pad the input, say with zeros, just to make it fit the network's expectations. Not the slickest solution, right? That's where transduction models swoop in, letting us feed the model variable length input and output sequences with ease. Now let's rewind to 2014. The introduction of a key paper showcased how recurrent neural networks, RNNs, could tackle variable length inputs and outputs. But here's the twist. The real champs weren't plain vanilla RNNs. Nope. The heavy lifting was done by fancier versions like long short-term memory, LSTM units, and gated recurrent units, GRUS. Before we dive more, why don't we explain what a language model is? Here's the idea. The model looks at a string of words like I want to and tries to predict what comes next. Eat, maybe? It does this by calculating the chances, or probabilities, of different words appearing based on what it's already seen. The first equation in the image breaks this down. The model figures out the probability of the whole sentence by multiplying the probabilities of each word given the words before it. For example, the chance of eat coming after I want to depends on the earlier words. To get good at this guessing game, the model trains on a bunch of example sentences. It tweaks its internal settings, called parameters, labeled as theta, to make its guesses better, aiming to maximize how likely its predictions are to match the real sentences it's trained on. This process is what the second equation is about. There's another concept we need to be familiar with, which is autoregressive models. Just like we described, most language models are autoregressive in nature. They generate one token at a time, and each token is conditioned on all its previous tokens. This sequential approach has its downsides. For one, we can't perform multiple operations in parallel. Plus, in simple models, RNNs in our case, they are more prone to long-term dependencies. More on that later. I'll drop a link to a video comparing autoregressive and diffusion models for image generation. Trust me, it's worth a watch. Now let's get back to our star paper. It points out the dominant sequence transduction models are based on complex recurrent or convolutional neural networks that include an encoder and a decoder. These encoder-decoder setups have been game changers in AI, even with a few tweaks along the way. Here's how they roll. The encoder reads an input sequence after the tokenization process, and the sequence can have a length of tx. Then, the decoder generates an output sequence of variable length, which can be ty. Want a clearer picture of sequence-to-sequence models? On the left, the encoder processes the input sequence token by token, then produces a vector that is packed with all the info and context, labeled HT. On the right, the decoder grabs that HT context vector to generate the first output token, and starts cranking out next output tokens, one by one. While digging into this paper, I came across a fascinating approach to machine translation. Picture this. You've got a source sentence, say, in English, and a target sentence in French. The researchers discovered something surprising. Reversing the source sentence significantly improved the model's performance. Their reasoning? It introduces many short-term dependencies into the dataset. Let's unpack that. In the encoder-decoder architecture, the encoder processes the input sequence, the English sentence, and compresses it into a fixed-size vector. Typically, this vector ends up emphasizing the last few words of the input because of how the model reads the sequence. By flipping the source sentence, the encoder sees the first word last. This means the encoder's final output, its fixed vector, has a stronger connection to the sentence's beginning, aligning it more closely with the decoder's first prediction. The paper offers a simple example to illustrate this. Imagine mapping the sequence ABC to alpha, beta, gamma, where A translates to alpha, B to beta, and C to gamma. When reversed, CBA feeds into the encoder, and A, now last, is closer to the decoder's first output, alpha. Then B aligns with beta, and so on. However, this is mere intuition with no proven evidence. The goal here is to estimate the probability of generating an output sequence given an input sequence. For example, translating a sentence from one language to another. Here's how it works. The encoder takes the input sequence, let's say a sentence in English, and processes it to produce a fixed-size vector representation, usually denoted as V. This vector captures the context or meaning of the entire input sequence. Then the decoder generates the output, one token at a time. First, it predicts the first output token, y sub 1 from V, then y sub 2 using V, and y sub 1, then y sub 3 using V, y sub 1, and y sub 2, and so on. Each prediction depends on the context vector V and all previously generated tokens. Finally, we multiply all the individual probabilities to get the full probability of the entire output sequence. This method works, but notice something important. There's a bottleneck. Everything from the input has to be compressed into one fixed vector. Here is a comparison table to make it clearer. On the left, we have the joint probability of a sequence, like in autoregressive models. This means the model predicts the next word based only on the previous ones, for example, generating the cat sat word by word. On the right, we have the conditional probability used in sequence-to-sequence models for translation. Here, the model looks at the input sequence and previous outputs to generate the next word. Remember the bottleneck that the encoder-decoder models had? That was the anchor of inventing the attention mechanism, as appears in this paper. The main issue was that it was difficult for the neural network to cope with long sentences, especially those that are longer than the sentences in the training corpus. A graph in the study drives this home. With standard RNN encoder-decoder models, the BLEU score, a metric for translation quality, drops as sentence length increases. On the other hand, an RNN with an attention mechanism is more prone to this type of issue. In RNN with an attention, we don't compress all the information into one fixed size vector, but instead, attention computes a weighted sum of the encoder's hidden states. At each decoding step, the model decides which parts of the input deserve focus. The result? Performance holds steady even with longer sentences. Here's where it gets even more interesting. The researchers used a bidirectional LSTM in this setup. Why? Think back to reversing the source sentence. It's all about creating short-term dependencies. A bidirectional LSTM takes this further. It processes the sequence in both directions. Each word can see not just the words before it, but also those after it, giving the model a richer understanding of the context. Before we proceed further, let's clarify the difference between deterministic search and neural search. On the left, deterministic search works like a hash table. Our query Q matches exactly one key, like K1, to retrieve its value V1. It's straightforward and precise. On the right, neural search used in self-attention mechanisms like transformers is more flexible. Here, Q matches all keys, K0 to Kn, to varying degrees. The result: a weighted sum of their values where the weights depend on how compatible Q is with each key. This allows models to capture richer context, which is super powerful for tasks like natural language processing. We can conclude from this abstract that we have three main objectives: minimize path length, reduce computational complexity, enable more parallelization. Now let's jump back to our main paper from 2016. It includes a detailed table comparing self-attention, recurrent layers, convolution, and restricted self-attention. Let's break it down. First, self-attention. Imagine a sequence of length n where each word or token is embedded into a d-dimensional vector. Since each word attends to all other words, the complexity scales with the number of interactions, O(n) squared. For the attention across all pairs multiplied by the embedding dimension d. So, the total complexity is O(n) squared times d. Second, recurrent. These process the sequence one step at a time. For each of the n positions, the hidden state, also size d, gets updated using a d by d weight matrix. Each update involves a matrix vector multiplication, costing OD squared. Repeat this n times, and you get a total complexity of On times d squared. Finally, restricted self-attention. This version limits each position to attending to only RR neighbors instead of all n positions. For each of the n positions, computing attention over R neighbors means R dot products of d-dimensional vectors, which costs OR times d per position. Across all n positions, that's ORND, a lighter load than full self-attention. The paper's architecture section explains the core idea. The encoder maps an input sequence of symbol representations, x1 to xn, to a sequence of continuous representations zd equals just z1 to zn. Given z, the decoder then generates an output sequence, e1 to ym, of symbols one element at a time. Here, symbol representations mean the input starts as discrete tokens, like words, which are converted into a continuous vector z, which is later processed by the decoder and turned back into a discrete output sequence, generating one symbol at a time. Let's build some intuition around residual connections, a cornerstone of this architecture. When we backpropagate through the network, the gradient flow reveals an interesting pattern. At an addition gate, like in a residual connection, the gradient splits evenly between the inputs, acting like a distributor. In a residual connection, the equation is simple. Output equals layer of x plus x, where layer could be a multi-head attention layer or a fully connected layer. Since the gradient is identical for both x and layer x, the network can decide whether to tweak the representation from layer or preserve the original input x. This flexibility can help ease the vanishing gradient problem in deeper networks. Let's zoom in on a key term, the compatibility function. The whole point of attention is to measure how well the query and keys are compatible. These compatibility scores become weights, which the model uses to search through different values and determine which ones it should attend to more. Multi-head attention can sound intimidating, but let's break it down with some variables we'll use later. CQ, the sequence length. D model, the size of the embedding vector. H, the number of heads in multi-head attention. dk and dv, the dimensions of the keys and values, usually the same. I want to focus more on the last paragraph. After tokenizing the input and adding positional embeddings, we create three copies of the sequence, which become the query, q, key, k, and value, v matrices. Each of these is multiplied by its own weight matrix to transform it. Crucially, these weight matrices are initialized independently. If they all started with the same weights, every head would focus on the same thing, boring and unhelpful. Instead, this setup lets each head zoom in on different aspects of the sequence. One might capture long-term dependencies, another might focus on short-term patterns, and yet another might pick up on syntax or structure. For a fantastic visual breakdown of how multi-head attention processes inputs and handles dimensions at each step, check out Umar Jamil's video on how transformers work. I can't recommend it enough. I encourage you to watch it.